This question is about how to find out the value for which the given system of equations have infinitely many solutions. The question is, consider the following system of linear equations: x plus 2y plus 3z is equal to 0, x plus py is equal to 0, and 3x plus 2y plus pz is equal to 0. We have the system of three linear equations. We need to find out the value or values of p for which the system of linear equations have infinitely many solutions is or options are being given. We need to find out the correct option or options. It is a multi-select question. Okay, so given the three equations here, first we write them into the matrix form, that is in this form, that is a x is equal to b. Okay, where a is the coefficient matrix, x is the vector of the variables x, y, and z, and b denotes the vector of constant terms. We write the given system of equations in matrix form first. Okay, so a is the coefficient, so let us write it like this. So in place of a we have 1, 1 and 3, 1, 1 and 3. Then we have 2, p, 2, so 2, p and 2, and then we have 3. Since z is not here, it is 0, and then we have p. So this is our a matrix. X is equal to x comma rather x, y, and z should be equal to the vector of constant terms, which is here 0, 0, and 0. Okay, so the condition is like this. So if we have if the determinant of this matrix is equal to 0, is not equal to 0, let me put it like this first, then we have a unique solution. Unique solution. If one condition, if the determinant of a is equal to 0, then there are two cases. Okay, that is another sub condition is there. If at least one numerator determinant is 0, we have infinitely many solutions. And if the determinant of a is equal to 0, and another condition is if none of the numerator determinant is 0, then we have no solution. Okay, sorry. So here we are supposed to go in this direction. Okay, so first we need to find out the determinant of this matrix, that is the determinant of the coefficient matrix. So we write 1, then delete the row and column in which it appears and take determinant of the remaining element. So we have 1 times p square minus 2 into 0 is 0. Then we have minus from the formula, then we write 2 and delete the row and the column in which it appears and take the determinant of the remaining element. So we have 1 into p, which is p, minus 3 into 0, which is 0. Then we have plus 3, and we delete the row and the column in which it appears and take determinant of the remaining element. So 2 into 1 is 2 minus 3p. Okay, for infinitely many solutions, this determinant should be equal to 0. Solve it, we get p square minus, here we get 2p plus 3 2s are 6, then we have minus 3 3s are 9p should be equal to 0, or p square minus 11 Okay, so let me see if I have done it correctly or not. So we have here p square minus 2p, 3 3s are 9, somewhere I have done a mistake. So here we have 3. Okay, so when we have 3, we delete this and this. Sorry, here we have 2x. Okay, I have already solved this question. So here we have 2x. So here we have 2. Okay, so then in this equation 2 2s are 4. Here we will get 4. Okay, I was wondering how did I got it incorrect. So here 3 4s are 12. So here we have 12. Okay, so we have 2 2s are 4 minus 3p. Okay, 3 3s are 9. Still I am getting confused here. Okay, let me take the determinant again. So determinant will be equal to, which will be equal to, so we write the first term, then we multiply. So delete this row and column. So determinant of this what we can say matrix. So it is p square minus 2 into 0 is 0. Then we have minus 2. We delete the row and the column. So 2 into p is 2p. Minus 3 into 0 is 0. Then we have plus 3. We delete this row and this column, rather this row and column. So take determinant of the remaining element. So 2 2s are 4 minus 3p, and it should be equal to 0. So we get here determinant of a will be equal to p square minus 2 into 2 is minus 4p. Then we have plus 3 4s are 12 minus 9p should be equal to 0. So p square, so 9 and 4, it is minus 13p plus 12 should be equal to 0. Factor this out. So we will get p square minus 12p minus p plus minus 12 times minus p. Okay, what we have done, we separated the middle term in such a way that the sum of the two numbers should be equal to 13 minus 13, and product of the same two numbers should be equal to 12. So if we write here minus 12 and minus 1, so it becomes minus 13. Minus 12 into minus 1 is plus 12. Okay, so let's take p common. We are left with p minus 12. Here we take minus p common. We are left with p minus 12, and it should be equal to 0. Let us take p minus 12 common. So here it is minus 1. Sorry, we have taken minus 1 common here. Okay, so then we are left with p minus 1 should be equal to 0. That means either p minus 12 is equal to 0 or p minus 1 is equal to 0, which gives us p is equal to 12 and p is equal to 1. Okay, so the values for which the given system of equations have infinitely many solutions, for that p should be equal to 12 and p should be equal to 1. So this option and this option should be correct. So we have tested only this condition here. Okay, we don't need to test this condition. For that, what we need to do, we need to solve the given system using Cranmer's rule. That is, first we need to find out another matrix, that is A1. So to find out the value of x1, what we do, we replace the first column of the coefficient matrix with the vector of constant terms. So we have 0 0 0 in place of 1 2 3. Then we have 2p 2, then 3 0 p. Okay, so this is A1. That is, this will give us, if we take then the determinant of A1, okay, then we will get the value of x1 will be equal to the determinant of A1 divided by the determinant of the coefficient matrix. Okay, this is what we call the numerator determinant here. And similarly for y, we need to form another matrix, that's A2, and we take its determinant and divide it by the coefficient matrix. And similarly for z, we form A3 by replacing the third column in this case and divided by the coefficient of matrix. So for infinitely many solutions, we should have two conditions. First, the determinant should be equal to 0. That is, we are done with the question, but I am explaining what is meant by the numerator determinant. So if at least one numerator determinant comes out to be 0, then we will have infinitely many solutions. We don't need to solve it further because we got the two values for which the given system of equations have infinitely many solutions. Okay.